Welcome to Calculus 1. In this lecture video, we're going to talk about concavity and the second derivative test. So far, we've been talking about, in our prior videos, we talked about relative minimum, relative maximum, the first derivative test, increasing, decreasing function. Alright, today first thing we're going to do here is talk about concavity. Alright, the concept is that the intervals in which f prime increases or decreases can be used to determine where the graph of the function f is curving upward or curving downward. Alright, so the idea of a concavity is saying that if I have a function f, it's differentiable on an open interval I. The graph of f is concave upward on the interval when f prime is increasing on the interval, and concave downward when the f prime is decreasing on the interval. And what we're going to notice that is concavity upward simply means that your graph function f lies above all the tangent lines, and f prime will give me the slope of a tangent line. So all these slopes will actually be above it, and that's how we know it's concave upward. Alright, concave downward means these tangent lines will actually be, the graph will actually lies below these tangent points or tangent lines. So to test the concavity, the way we do it is by saying if f of double prime, let's take a derivative twice of the function. If f double prime of x is greater than 0, for all the x's in the interval I, then the graph is concave upward. So if f double prime is less than 0, then the graph of the function is actually concave downward. So here we'll actually need to take two derivatives. Let's try an example here. Determine the open interval on which the graph is concave upward or downward. So let's take the first derivative of my function. So f prime of x. So this is derivative of e. Derivative of e to the u, as you can recall, is going to be e to the u times u prime. So I'm going to let my u to be negative x squared over 2. Alright, so the first derivative, e to the u, so that will be still going to be e to the negative x squared over 2 times u prime. My u got to be, take a derivative of, so that will be negative half still up front, bring the x squared down, and then exponent decrease by 1, so that will be x to the first. If I simplify this is going to cancel out, so that will just leave me with negative x times e to the negative x squared over 2. Alright, so that's f prime. So if I set this equal to 0, I can find my critical point. Alright, let's do an f double prime. Take the second derivative so I can see if I'm concave up or concave down. Alrighty, so here to take another derivative of this negative x, I'm going to say the first one is negative x, the second one is e to the negative x squared. So derivative of the first, which will be negative 1, times the second, still the same thing, plus derivative of the second, which is derivative of this, will give me the same answer right here. Derivative second times the first. The first one is still going to be negative x. Alright, so I'm going to simplify this before I'll set it equal to 0. Both term has e to the x here. So I can factor that out just in a minute. So this is going to be negative e to the negative x squared over 2 plus x squared e to the negative x squared over 2. Alright, so what I'm going to do here is I'm going to factor out, I'm going to go ahead and set this equal to 0, but I'm going to at the same time factor out a negative e to the negative x squared over 2. Move this down a little bit. Alright, so if I factor out a negative e between these two terms, what will be left? This term will be a positive. This term will be a negative x squared. Okay. Excuse me. Oops. Oh, I don't. No, excuse me. I'm not going to factor out a negative. I'm actually going to factor out a positive because it's easier for me to solve for 0 that way. If I factor out positive, that means this is still going to be x squared. This term was a negative, so this one will become a negative 1. So take this out. So leave me with x squared. I'm going to put up front. This term will have a negative 1. Because in this case, I can easily set equal to 0 and help me solve. If I set this factor, e to the negative x squared over 2, to set equal to 0 and solve for x, alright, and then x squared minus 1 is x plus 1 and x minus 1. So I know my answer. I'm gonna actually have an x equal to 1 and x equal to positive 1. Alright, so over here, to get rid of the e, I gotta take a natural log on both sides first. So natural log of a 0 is actually undefined. So I cannot really solve for x here. In other words, this e to negative x over 2 actually cannot really be equal to 0. So here I got 2 points. One is positive 1, one is negative 1. Alright, so let's take a look at the intervals. Okay, from negative infinity all the way to negative 1, I'm gonna use negative 2 to test with. So my f double prime of negative 2, alright, plugging negative 2 back into my f double prime. Okay, and if you plug it in, you will notice the y value will be positive. So if it's positive, that means I'm concave upward in that interval. Alright. Testing between the interval of negative 1 to 1, I'm going to use 0 for my testing point. Alright, if I plug in 0 here for x squared, 0 here, or I can use it for this one here. Okay, plug in 0 there. I believe I will actually, my y value will be less than 0. So they tell me that it will be concave downward. Alright. To the right side of this 1. So from 1 to infinity, I'm going to use a positive 2 as my testing point. So f double prime of 2. Alright, plug in 2 back into my f double prime, and I believe that the y value will be a positive number. So that means in that interval, okay, my graph is concave upward. Alright, so that's how we test for concavity. And the testing for concavity also leads to, will also relate to second derivative test. I'm going to introduce this in a minute. Alright, let's look at this example here. It's a little bit different. Alright, for the interval where where the function concave upward or downward. So I'm going to take a derivative of my function. Alright, derivative of the top times the bottom minus derivative of the bottom times the top over the denominator squared. Alright, using quotient rule. Alright, let me kind of clean this up a little bit. This is going to be 2x to the third minus 2x to the third. That cancels out. Negative ax minus 2x negative 10x over x squared minus 4 x squared. Alright. Now I'm going to take another derivative of my f prime. So f double prime this real quick. Derivative of the top, that'll just be negative 10 times the bottom, minus derivative of the bottom, and my derivative of the bottom is a composite function, so derivative of the outside times the inside times the derivative of the inside, which is just 2x. So that's derivative of the bottom times the top, which is negative 10x. Whole thing over. The bottom squared again. Alright, this is quite a mess. Alright, this negative and that negative will make a positive. Let's see. So my second term is positive. Both of these terms has x squared minus 4. Okay, this is to the first power, that's the second power. So I'm going to factor out x squared minus 4 to the first power. Alright, and both terms has 10. I'm going to factor out a 10. So that will leave me with, okay, factor out the 10 and this one of these right here. So that will leave me with negative x squared minus 4 plus this negative makes a positive here. Take out the 10, so that will be 2 times 2 is 4. X times that x is x squared. Take this thing outside, so that just be 4x squared here. Oh, I'm sorry. Squared again will be 4 power here. Make sure it's x minus 4. Alright, negative x squared plus 4x squared will give me 3x squared. Negative 1 times negative 4, positive 4. And I will, and my x squared minus 4, after I factor out, can cancel it out with one of these down here. So that I have a 10 on top over x squared minus 4 to the third power. Alright, so this is my f double prime. Alright, so I want you to look at this. If I set my f double prime equal to 0, I just want you to look at it. It's actually not gonna work for me because I actually cannot solve for x. Set at 0 over 1. So cross product, that will be 0 times that will be 0. Set it equal to the top times 1, still the same thing. So if I was set my 3x squared plus 4 equal to 0, if I set this factor equal to 0, I actually gonna end up with imaginary numbers. Okay. Alright, so that tell me that I cannot use, let me go back up to the top. That tell me I cannot actually use this test for concavity. Alright. So no points. I actually do not have any point. I'm gonna go ahead and erase this. So it turns out there's no points. At f double prime of x that's equal to 0. I actually don't have none of those. Alright, but here's a good thing. Alright, since f is actually not continuous, at x equal to positive negative 2, I can actually use that positive negative 2, okay, to help me, alright, to help me to see whether I'm concave up or concave down. So where do I get this notion of x, okay, f is not continuous at x equal to 2 and x equal to negative 2? Well, because if you're really looking back, okay, if you're really looking back at all the denominator, okay, those x's cannot actually be 2 or negative 2. X squared minus 4, if I set that equal to 0, that's x plus 2 times x minus 2. So my x is equal to 2 and x equal to negative 2. Now the square just tell me I have two sets of the same answer. Okay, so that tell me that my function is not continuous back in the f prime, okay, at these 2 points. So I can use that opportunity to help me to evaluate or help me to do my test. Okay, because I don't have f double prime of x. Alright, so from the f prime, the interval from negative infinity to negative 2, okay, I can use f double prime. I'm going to use negative 3 for my test. Alright, in between negative 2 to 2, I can pick a number for testing value. I'm going to pick 0 this time. And then from 2 to infinity, okay, my f double prime, I'm going to choose positive 3. So if I plug in these 3 test numbers back into my f double prime, and you will see f double prime negative 3 will be a positive value. So that tells me it will be concave upward. F double prime of 0 is going to be negative, so that tells me it's concave downward in that interval. Alright, and at f double prime of 3, it will be a positive y value. So that means it will be concave upward. So a lot of times, if it helps, graph the function. Okay. Graph the function. That'll definitely be a big help. Remember, upward, concave upward means all these tangent lines, okay, it's gonna be lies right underneath the graph. Okay. A lot of students look at these weird concave downward means the tangent lines is actually on the top. Okay. Alright. And sometimes that, you know, the graph can actually go from concave up and concave downward. In such case, okay, if I where do I go from upward to downward? Okay, and that point is called the point of inflection. Okay, a point of inflection is when the graph changes from concave upward to concave downward. So I can concave downward, and all of a sudden I can actually begin to concave downward. And don't be mistaken. Okay, you have a relative minimum maximum here. Okay, so these tangent lines are still lying below the graph, but all of a sudden there's a point somewhere between the two concavities where you'll switch over to become concave downward. So we will need to find that point, and that's what this objective is about. So, point inflection, if the point C, comma FC is a point of inflection, okay, then either f double prime of C is equal to 0 or f double prime does not exist at x equal to C. So basically we can come back to this last problem. I could not solve for if there's no point to f double prime of x. Okay, so that means I couldn't find my points of inflection at C. Alright, so it's not hard. Certain graph you got, certain graph you have point inflection, certain graph you do not. Okay, so I'm gonna first graph this function here first. Right. X to the 4th minus 4x to the 3rd. Alright, so here's my polynomial function. Okay. This graph go down and then curve back up. Alright, I'm gonna just leave it on my calculator. Let's do my derivative. Okay, this is f double prime of C. So my first f prime of x is gonna be 4x to the 3rd minus 12x squared. Alright, if I set equal to 0 now, they'll find me in the critical point. Okay, but I need to do f double prime. F double prime will be 12x squared minus 24x. Alright, set this equal to 0. I'm gonna go ahead and factor out my 12x as well. So that's x minus 2. So if I set 12x equal to 0, x equal to 0, and this one set equal to 0, x equal to 2. Right. So now, this 0 right here, if you think about the interval from negative infinity all the way to 0, if I would pick -1 as a test point, plug it back into my f double prime, it will actually be a positive. So that tells me it's concave upward. And let's say up. Between the two interval from 0 to 2, alright, use f double prime of 1. It's going to be negative, so I'm concave down. Alright, from 2 to infinity, f double prime of 3 will be a positive. So that means concave upward. Alright, so what that tells me is, let me look at the graph real quick. I'm going to make it a little bit smaller. Go from -5 to 5. I'm going to go down a little bit more to -30 to 10. So maybe I can see that bottom right there. Alright, so what that tells me is, okay, at 0, okay, point x equal to 0, the left side of it at -1 is concave up. Alright. F of 1, after I pass 0, f of 1, it begin to concave down. So between up and down, okay, that means there's got to be a point of inflection, which is my 0 is the point of inflection. Alright. So from 1 to 2, okay, so from 1 to 2, excuse me, from 2 and on. So if I go down from x equal to 2 down here. Alright. So remember now, before 2 I was concave downward. Alright. When I do my 3, it became concave upward. So that means at my point 2 here, the graph switch over from concave down to concave up. So that will make my x equal to 2 as a point of inflection. Okay, so that's what these two numbers are. These two are the point of inflection. Okay, so it's kind of easier. I mean, you can't really see it, okay, just by looking at the graph. That's why we still do these computations. Alright. Now if I go back to f prime, okay, factor out of 4x squared, and that will leave me with x minus 3. Set it equal to 0 to find my critical point. So I got a critical point at 0 and 3. So my graph kind of confirms it. Okay. Make sure it's right there. I have a relative minimum, okay, at 3 down here. Okay. Alright. So it turns out the second derivative test, okay, can actually be a simple test for the relative minimum and maximum. It actually tells us that those are the relative minimum or maximum. Okay, so this is kind of weird. The test is based on the fact that if the graph of function concave up on an open interval containing C and f prime of C equal to 0, then f of C got to be a relative minimum. So if I concave upward, wherever my f prime of C is equal to 0 at, that tangent line right there got to be the relative minimum. Okay, that's what this test is based off on. So the condition here for the second derivative test is let f of b, let the function f be a function such that f prime of c is equal to 0 already. Alright, so this c right here is actually the x value coming from the f prime. And the second derivative of f exists on an open interval containing c. So if f double prime of c is greater than 0, there is a relative minimum. If f double prime of c is less than 0, there's a relative maximum. If f double prime of c equal to 0, then the test fails. We're going to go back and use the first derivative test. So let me show you how it works. Okay, this is not hard. We got to find this c first before I can actually use it for the second derivative test. Alright, so first thing first, f prime of x. The first derivative will give me negative 15x to the fourth plus 15x squared. If I set this thing equal to 0, I'm going to go ahead and factor out my negative 15x squared, and that leaves me with x squared minus 1. Alright, so x squared is equal to 0, x equal to 0. X squared minus 1 is x plus 1, x minus 1. So say each one equal to 0 is 1 and negative 1. Alright, so these are my critical numbers. Okay, and these are my c. Alright, second derivative test. second derivative of the function is negative 60x to the third plus 30x. I'm gonna set, okay, I'm not gonna set this equal to 0, okay, because I'm not trying to find concavity. Instead, what I'm gonna do here is go back and look at my critical value, okay, -1 for x, okay, is this -1, alright, a relative minimum or maximum? That's what I'm trying to find out. Alright, if I take this -1, go back, plug it back into this function, I believe the y value is 2, so is this point relative minimum or maximum? And to see that, we got to plug in a test value into the f double prime. Alright, and this test value is the critical number itself. These c are the critical numbers coming from f prime of c. So I'm going to plug in -1. Then obviously my y value is positive. So that tells me that this point is relative minimum. Alright, I'm going to do +1 right now. If I plug in +1 back into the original function, y value is another 2. So that means f double prime of my c, okay, well, let's see if it's positive. And this is the weird part. I'm going to put in the calculator and check it out. F double prime of 1. So that's going to be -60. 1 to 30 is still 1. -60 plus 30 times 1 is 30. Ooh, this time is -30. So my y value is actually negative. Okay. But y is here positive because this is not looking at the y value here. This 2 is coming from the original function. We need to plug in the -1 back in here. Alright, so if it's less than 0, that's relative maximum. Alright. So make sure y'all do see my notation. F double prime, F double prime. When I say this is +0, I'm looking at the 2, but this 2 actually comes from the original function f. But this is the f double prime. The y value here I'm looking at got to coming from this function. Okay, so I just want to point out, a lot of times, we tend to look at the wrong spot. When we actually plug the number back in. So make sure we notice these, which one of these functions we need to go back to. Alright, another critical number is 0. That's between -1 and 1. If I plug in 0 back in the original function, I believe the y value is 0. So f double prime of 0, okay, my critical number, 0 here, 0 there, will still equal to 0. So that means the second derivative test is fails. So in such case, we can use first derivative test. Alright, and the first derivative test, if I go back to the first derivative test, alright, if f prime of x changes from negative to positive at that critical point C, f has a relative minimum. Okay. So, if I go back to the first derivative test and just do what I've done before, looking at those interval thing. Alright. I'm going to use f prime, because I'm thinking about 0 here. To the left of 0 is -infinity to 0. I'm going to pick a number close, that will be -half. The other interval will be from 0, then go to the right, So I'm going to use f prime of a half because I don't want to get into the 1 or negative 1. So if I take negative half and plug it back into my f prime using the first derivative test, my y value will be positive. Alright. If I take half, okay, back into my f prime, alright, my y value will still be positive. So what that tells me is, if I go back to this, if f prime is negative on both sides or positive on both sides of c, then it has then that's neither relative min or relative maximum. So at a critical point 0, okay, to the left is greater than 0, to the right is also greater than 0. Okay, therefore, since it's positive on both sides of my critical number, that means what? 0, 0 is actually neither relative minimal or nor relative maximum. So my only relative minimum maximum is at negative 1, 2 and at 1, 2 for this problem, for this function. Alright, so and that will conclude our first, second derivative test, relative, and the extremeless. Okay. The next video, we're going to talk about limits at infinity. Okay, and that will take us into another set of materials where we will use limits at infinity.